Hi everyone. First of all, I would like to thank everyone for watching my previous video on global illumination. I really appreciate your comments. So today I am showing you how to create a terrain using DirectX 11. So when I had started my career, I was working on DirectX 9. My senior had created a really good terrain, but that system faced two problems. One is FPS and second one is detail of the terrain. If you want more details on the terrain, you need to generate more and more vertices, will consume more and more memory, and which in turn will kill your FPS. So DirectX 11 we have two techniques known as hardware instancing and tessellation. So I'll show you how I'm generating the terrain using these two techniques. So the root of my system is a quad which is 100 into 100 meter. This actually holds the vertex buffer. So I'm generating three levels of LOD. LOD 1 which consists of 8 into 8 64 vertices, LOD 2 4 into 4 16 vertices, LOD 3 2 into 2 4 vertices. So at total I have 84 vertices, and I am allocating memory only for those 84 vertices in CPU. Now I have another class which is a terrain grid, which is a 1 into 1 kilometer. So each holds the information of the positions where I want to generate each quad. So and then in terrain manager I have two functions. One is pre-render where I am generating the LODs depending on the distance from the camera. So then pushing all these LODs to a list. Actually I got three lists for each type of LOD. Then I am using hardware instancing to render those LODs. So I'll show you the instruction is draw indexed instance. Using this instruction we can draw indexed triangles. So actually in this case since I am using tessellation, I am using a topology of 4 control point patch list, which is actually a quad consists of 4 points. So I'll show you the output, then I will tell you a few things about tessellation. So now this is a terrain. This is a 4 square kilometer terrain. I have scaled it down a bit so that I can show you the entire terrain. So this whole terrain is generated out of 84 vertices, but the total terrain vertices count which is shown in the screen is above around 5 lakh. Actually, because all these vertices are generated using tessellation, so the number of vertices what's showing here is actually are in GPU. So you can see at 7 lakh vertices, but still the system is running at 60 FPS. It might be a bit jerky because of my recording. So you can see the detail of this terrain. You can see the bump at each point, actually height and shadow, lighting, everything is calculated in runtime. And the shadow is at very primitive level as I have not worked on that much. So I'll show you the grid mode, the amount of vertices I am generating in runtime. I cannot show the entire terrain, so I'm showing you just one corner. You can see around right now it consists of 804 vertices. So I just enable the grid mode. You can see these vertices. It's just at the small portion of the terrain I have 800 and some 800 700 813 vertices. So still the system is running at 60 FPS since I'm not allocating any memory for all these vertices in CPU. So you can see this whole terrain. As we'll go away from the terrain, your vertex count will change as the LODs will change. So this is that kind of a cutoff thing out of my camera view. So you can see all these vertices. It's kind of a zero when everything goes down. So I'll show you the instructions of tessellation, how I'm generating this large amount of vertices on GPU. So this is my FX class. So tessellation consists of three parts. One is Hall shader, one is tessellator, one is domain shader. So Hall and domain shader are programmable pipelines. You can write your own code, but tessellator stays, it's still a fixed function pipeline. So this is my Hall shader. This is my Hall shader. This is the format of writing a hall shader. It contains a patch constant function. So in patch constant function, actually I am generating the tessellation amount. This amount is assigned to each edge, and tessellator will generate the new points according to that amount. So I'll go to this function clamp to smaller adjacency side. So here I am using tessellation amount from projected circle. This is very simple logic. I am just taking two vertices, calculating the distance between two vertices in screen space. Then I am allocating a tessellation amount to that. I am converting the tessellation amount to power of a 2. I don't know, it only works when I make them power of 2, otherwise I did not get the desired result. I get kind of a gap between each grid, so I make it like that. After the tessellation hall shader, the tessellator stage will generate all those control points, and in domain shader I'll assign position to all those points. Once the position is generated, I took the height map value. I used two level of height map. One is overall height map, one is very detailed height map. So all these height maps are calculated here, and they assign this height map value is assigned to each vertices. After that, usual pixel shader will transform all these vertices and calculate just the normal and the color value. So this is how the rendering part is done. The second part is collider. So as you know, I generated all these vertices in GPU. There is no way I can access it in CPU. So, but DirectX 11 provides a very good technique known as streaming buffer, where I can stream out all those vertices from GPU to CPU so that I can access it. I can save it and use it for any kind of future calculation. So collider is also generated from same level of LOD, but it doesn't use any tessellation. It's just the LOD and hardware instancing. So I'll just render the collider right now so that I can see how it looks like. Now this is the collider, the grid part. It covers the terrain. It's not exactly 100%, but it almost covers this terrain. If you increase the LOD count, it will cover more properly. So you can see still the system is running at 60 FPS even if I have generated terrain, collider, and also the terrain. So next step is do the raycasting. As you know, raycasting is a very important technique, because you want to put a tree or generate a vegetation system or foliage system. We need to get the raycast at each point, and raycasting is a very simple, is a very slow process on CPU, because I have some 5 lakh vertices. It consists of maybe some 2 lakh to 3 lakh triangles, and if you do that kind of calculation on CPU on 2 lakh triangles, it's practically impossible. It's not impossible, it's very slow. It will kill your FPS. So I'm using compute shader. So whatever vertices are generated in quad collider, so I just pass them to a ray tracing compute shader. This shader will calculate the ray tracing part. It will take each point, calculate the intersection point, and then it will see whether the point is inside the triangle or not. So I am using the same side formula, like if the point is on the same side of all these 3 vertices, it's inside the triangle. This is the function who do all this calculation. It's a very simple logic. You can get all this mathematical explanation on net. So after I get the value, I save that value in this buffer. It's a kind of a random access buffer. So it's right now it stores only a single value, because raycast will give you output only 1 point actually. So once I get that value, I stream out this value to, I did not stream out actually, I can directly access this buffer. I use this value in CPU. So I can store it in CPU, I can use it for later purpose, I can show it on screen, something like that. So I'll show you the output of raycasting, and I can see the FPS. So I'll just enable the raycasting. You can see the raycast value is changing frequently as I am moving, height, XYZ value, and still the system is running at 60 FPS. So it's really cool to do all these three things, and even if system is running at 60 FPS, DirectX provide really this good technology. So thanks all for watching this video. I'll post some new videos on DirectX 11 pretty soon. Thanks.